Welcome to week 7 of Fundamental of Python and Machine Learning. In this lesson, we are covering Chapter 7, Supervised Learning Classification using Logistic Regression. During the previous chapter, we used regression to predict numerical values. This week, we will move from numerical prediction to classification. Logistic regression estimates the probability that an observation belongs to a class. We can then use that probability to make a class prediction. We will study the ideas behind logistic regression, train a model using Scikit-learn, make probability and class predictions, and evaluate the results using a confusion matrix precision recall F1 score and the ROC curve. By the end of this chapter, you should be able to explain how classification differs from numerical regression. You should understand how logistic regression produces probabilities between 0 and 1, and how a threshold converts those probabilities into class predictions. You will learn the meaning of odds, log odds, and the sigmoid function. You should also be able to load and inspect the Breast Cancer Wisconsin Diagnostic dataset, identify its features and target classes, preserve class proportions when splitting the data, and train a logistic regression model using a Scikit-learn pipeline. Finally, you will learn how to evaluate classification results using a confusion matrix, accuracy, precision, recall, F1 score, the ROC curve, and area under the curve. Classification is a supervised learning task. The training data contains input features and known class labels. The model learns patterns that help separate or distinguish those classes. After training, the model receives a new observation and predicts the class to which that observation most likely belongs. Examples include spam or not spam, approved or denied, fraudulent or legitimate, and benign or malignant. The defining characteristic is that the output is a category rather than a continuous numerical value. Linear regression and logistic regression solve different types of problems. Linear regression predicts a numerical value, such as a house price or final score. Its output can be any real number. Logistic regression is used for classification. It estimates the probability that an observation belongs to a class. That probability is constrained between 0 and 1. Although its name includes the word regression, logistic regression is commonly used as a classification algorithm. Instead of feeding a line directly to class labels, it transforms a linear score through the sigmoid function and produces a probability. Binary classification contains two possible classes. A logistic regression model estimates the probability of one selected class, often called a positive class. If the estimated probability is close to 1, the model considers that class more likely. If it is close to 0, the other class is more likely. For example, a model might estimate an 82% probability that an observation belongs to the malignant class. The probability provides more information than the final class label because it shows how strongly the model favors one outcome over the other. However, the probability is a model estimate, not certainty. To convert a probability into a class, we use a classification threshold. A common default threshold is 0.5. With this threshold, probabilities below 0.5 are assigned to one class, while probabilities at or above 0.5 are assigned to the other. In binary logistic regression, Scikit-learn's predict method selects the class with a greater estimated probability. This normally corresponds to a 0.5 decision threshold. The threshold is a decision rule, not a law of nature. Changing it affects the number of false positives and false negatives. For high-stakes applications, the threshold should reflect the consequences of each type of error. Odds compare the probability that an event occurs with the probability that it does not occur. The formula is probability divided by 1 minus probability. If the probability is 0.5, the odds are 1. This represents equal odds. If the probability is 0.75, the odds are 3, meaning the event is estimated to be 3 times as likely to occur as not occur. If the probability is 0.2, the odds are 0.25. Probabilities are restricted between 0 and 1, while odds range from 0 toward positive infinity. The logit function takes the natural logarithm of the odds. It transforms a probability between 0 and 1 into a value that can range from negative infinity to positive infinity. A probability below 0.5 produces negative log odds. A probability of 0.5 produces log odds of 0. A probability above 0.5 produces positive log odds. Logistic regression models these log odds as a linear combination of the input features. This connection allows the model to begin with a linear score while still producing a valid probability. The sigmoid function performs the reverse transformation. It takes any real number score and converts it into a value between 0 and 1. Very negative scores produce probabilities close to 0. A score of 0 produces a probability of 0.5. Very positive scores produce probabilities close to 1. The sigmoid has an S-shaped curve. The center of the curve changes quickly, while the two ends approach 0 and 1 without extending beyond those limits. This makes the sigmoid useful for turning a linear model score into a probability. Logistic regression begins by calculating a linear score. The score equals the intercept plus each feature multiplied by its coefficient. We represent this score with the letter z. The sigmoid function then transforms z into the estimated probability that the observation belongs to class 1. Beta 0 is the intercept, each beta value is a learned coefficient, each x value is an input feature. With one feature, we can visualize the model as a sigmoid curve. With multiple features, the model creates a decision boundary in a higher dimensional feature space. The textbook explains logistic regression using maximum likelihood estimation. The model searches for coefficients that make the observed training labels as likely as possible. This process is closely connected to minimizing a loss function called Scikit-learn. Logistic regression also applies regularization by default. Regularization discourages excessively large coefficients and can help the model generalize more reliably. Therefore, the practical Scikit-learn estimator learns parameters by optimizing a regularized or penalized logistic objective. The important idea is that the coefficients are learned from the training data rather than selected manually. This chapter uses the Breast Cancer Wisconsin Diagnostic dataset. It is a binary classification dataset included with Scikit-learn. The dataset contains 569 samples and 30 numerical features. 212 samples are labeled malignant and 357 are labeled benign. The features were computed from digitized images of fine needle aspirates of breast masses. This dataset is appropriate for learning classification techniques, but it is not a clinical diagnostic system. Our model and examples are for educational purposes only and must not be used to make medical decisions. The dataset contains 30 numerical measurements. Examples include mean radius, mean texture, mean perimeter, mean area, and mean smoothness. Additional columns describe the standard error and the worst or largest values for related measurements. The original Scikit-learn target encoding uses 0 for malignant and 1 for benign. This mapping is important. We should never assume what 0 and 1 mean without examining the dataset's target names. The numeric codes are labels. They do not imply that one class is more important than the other. We load the dataset using load breast cancer from Scikit-learn datacells. By setting as frame to true, Scikit-learn returns the features and target using pandas objects. The complete frame contains all 30 feature columns and the target. We can use familiar pandas methods such as head, shape, info, describe, and is null to inspect the data. We can use familiar pandas methods such as head, shape, info, describe, and is null to inspect the data. We inspect target names to verify the meaning and order of the target labels. We also count the observations in each class. The dataset contains more benign examples than malignant examples. This is not an extreme imbalance, but the classes are not evenly distributed. Class proportions matter when splitting the dataset and interpreting accuracy. A model that performs well for the more common class may still perform poorly for the less common and more consequential class. This is one reason classification evaluation requires more than a single accuracy number. Terms such as positive, negative, true positive, and false negative depend on which class we define as positive. Scikit-learn's original dataset uses 0 for malignant and 1 for benign. However, many binary classification metrics treat label 1 as the positive class by default. For this lesson, we will recode the target so that 1 means malignant and 0 means benign. This makes recall for the positive class represent the proportion of malignant cases detected by the model. Recoding is not required to train logistic regression, but it makes our medical error discussion and metric formulas easier to interpret. The class definition must always be documented clearly. Visualization helps us examine how the classes relate to selected features. For example, we can plot mean radius against mean texture and style, the points according to the target class. We may notice regions where malignant and benign observations are more common. We may also notice overlap. Overlap is important because it shows that no single feature perfectly separates the classes. A three-dimensional scatter plot can add another feature, such as mean perimeter. However, visualizations with 2 or 3 features represent only part of a dataset containing 30 features. Capital X contains the 30 numerical input features. Lowercase y contains the recoded target. Each row in X corresponds to the target value in the same row of Y. Our goal is to train a model that uses the feature measurements to estimate the probability that an observation belongs to the malignant class. Because the feature columns have different units and ranges, we will include feature standardization as part of the modeling pipeline. We divide the dataset into training and testing subsets. In this example, 75% is used for training and 25% is reserved for testing. The stratified parameter preserves approximately the same class proportions in both subsets. Without stratification, a random split could place too many examples of one class in the training or testing set, especially with smaller or more imbalanced datasets. The random state makes the split reproducible. The testing data remain separate from model fitting and pre-processing so that it can provide a more honest evaluation. The feature columns use different numerical scales. Standard scaler centers each training feature around 0 and scales it using the training standard deviation. Logistic regression often benefits from standardized features, especially when regularization is used. We place a standard scalar and logistic regression inside a pipeline. The pipeline ensures that the scalar learns only from the training data. When we later predict on the test set, the same training-based transformation is applied automatically. This helps prevent data leakage and keeps pre-processing consistent. To understand the model visually, we can begin with one feature, such as mean radius. We split the one feature dataset, build the same scaling and logistic regression pipeline, and fit the model. We can then calculate the malignant probability for a range of radius values. When plotted, the probabilities form a sigmoid-shaped curve. Smaller values may produce lower malignant probabilities, while larger values may produce higher probabilities. The exact relationship is learned from the training data. This one feature example is useful for visualization, but a practical model can benefit from the information contained in multiple relevant features. The fitted classifier provides an intercept and a coefficient. The intercept represents the model score when the standardized feature value is 0. The coefficient determines how the log odds change as the standardized feature increases. A positive coefficient means the estimated probability of the positive class increases as the feature increases. A negative coefficient means it decreases. Because the pipeline standardizes the feature, the coefficient describes change in relation to standardized units rather than the original measurement unit. Coefficients describe associations learned by the model. They do not prove that a feature causes the outcome. We now train the complete model using all 30 features. The pipeline first learns the mean and standard deviation of each training feature. It transforms the training data and passes the standardized values to logistic regression. The classifier then learns an intercept and one coefficient for each feature. The model combines all feature contributions into a linear score and converts that score into a malignant probability using the logistic function. After fitting, the pipeline is ready to generate probabilities and class predictions for the unseen test set. The predictor proba method returns one probability per class. The columns follow the order shown by the classifier's classes property. In our recorded target, class 0 means benign and class 1 means malignant. Therefore, the first probability column represents benign and the second represents malignant. The two values for each observation add to 1. We should never assume which probability column represents which class. Always inspect classes and document the mapping. Probability estimates can support threshold decisions, but they should still be evaluated for discrimination and, when necessary, calibration. The predict method returns the final class label for each test observation. For binary logistic regression, the selected class is the one with the greater estimated probability, with the usual 0.5 threshold. A malignant probability of 0.81 becomes class 1 malignant. A probability of 0.19 becomes class 0 benign. The predicted class is convenient, but it hides the underlying probability. For evaluation and threshold analysis, we often need both the class predictions and the probability scores. A confusion matrix compares actual classes with predicted classes. Because we recoded benign as 0 and malignant as 1, the standard matrix arrangement is easy to interpret. A true negative is an actual benign case correctly predicted as benign. A false positive is an actual benign case incorrectly predicted as malignant. A false negative is an actual malignant case incorrectly predicted as benign. A true positive is an actual malignant case correctly predicted as malignant. The confusion matrix shows the kinds of mistakes the model makes, not only the total number of correct predictions. The word positive does not mean healthy, desirable, or correct. It means the class we selected as positive for evaluation. If malignant is the positive class, a true positive is a malignant case correctly identified as malignant. A false negative is a malignant case incorrectly predicted as benign. If we instead define benign as positive, the meanings of true positive, false negative, precision, and recall change. This is why class encoding and positive class definitions must be stated explicitly. Metric values can be misunderstood when the class mapping is hidden or assumed. Accuracy is the proportion of all predictions that are correct. We add the true positives and true negatives and divide by the total number of observations. Accuracy is useful as a general summary, but it can hide important problems. If one class is much more common, a model can achieve high accuracy while performing poorly on the less common class. Accuracy also treats false positives and false negatives as equally costly. In many real situations, those errors have different consequences. Therefore, accuracy should be interpreted together with the confusion matrix and class-specific metrics. Precision focuses on the observations predicted as positive. With malignant defined as positive, precision asks, of the cases predicted malignant, how many were actually malignant? High precision means that relatively few benign observations were incorrectly classified as malignant. The denominator contains true positives plus false positives. Precision is especially important when false positive decisions carry significant cost. However, a model can increase precision by making fewer positive predictions, which may reduce recall. The two metrics should be considered together. Recall focuses on the actual positive observations. With malignant defined as positive, recall asks of the actual malignant cases, how many did the model correctly identify? The denominator contains true positives plus false negatives. A false negative occurs when an actual malignant observation is predicted as benign. In a medical screening context, this type of error may be especially concerning because the model fails to flag a potentially serious case. However, the appropriate trade-off must be determined by qualified medical, ethical, and operational experts. Our educational model does not establish a clinical decision threshold. The F1 score combines precision and recall into one measurement. It uses the harmonic mean, which gives a low score when either precision or recall is low. F1 can be helpful when we need a balance between detecting positive cases and avoiding incorrect positive predictions. However, F1 does not include true negatives directly. It also assumes that precision and recall should receive equal importance. A single summary metric cannot determine whether a model is appropriate. The choice of metric should reflect the problem, the class definitions, and the consequences of different errors. Scikit-learn's classification report summarizes precision, recall, F1 score, and support for each class. Support is the number of actual observations belonging to that class. The report also includes overall accuracy and averages across classes. The macro average calculates the unweighted mean across classes. The weighted average gives greater influence to classes with more observations. Examining both rows helps us avoid focusing on only one class. Before interpreting the report, verify that the target names appear in the same order as the numerical labels. The receiver operating characteristic, or ROC curve, evaluates the classifier across many possible thresholds. The vertical axis is the true positive rate, which is the same as recall. The horizontal axis is the false positive rate. Each point on the curve represents a different threshold and a different trade-off between detecting positive cases and creating false positives. A curve closer to the upper left corner indicates stronger class separation. The diagonal line represents performance similar to random ranking. The ROC curve evaluates discrimination across thresholds rather than committing to only the default threshold of 0.5. Area under the curve, or AUC, summarizes the ROC curve with one value. An AUC of 1 represents perfect ranking of positive observations above negative observations. An AUC near 0.5 represents ranking similar to random guessing. AUC measures discrimination across thresholds, but it does not select the threshold for us. Lowering the threshold usually increases recall because more observations are classified as positive. It can also increase false positives. Raising the threshold may reduce false positives but increase false negatives. The appropriate threshold depends on the consequences of each error, available resources, ethical requirements, and domain expertise. AUC is useful, but it should be interpreted with the confusion metrics, class balance, and the intended use of the model. Let's summarize Chapter 7. Logistic regression is a supervised learning algorithm used for classification. It calculates a linear score and transforms that score into a probability using the sigmoid function. A threshold converts the probability into a predicted class. We loaded and inspected the Breast Cancer Wisconsin Diagnostic dataset, examined its feature columns and target labels, and explicitly defined malignant as the positive class for our evaluation. We created a stratified training and testing split, standardized the features inside a pipeline, and trained a logistic regression model. We used predict per boa to obtain class probabilities and predict to obtain final class labels. We evaluated the results using a confusion matrix, accuracy, precision, recall, F1 score, a classification report, the ROC curve, and AUC. The most important lesson is that no single metric tells the complete story. Class definitions, probability thresholds, class balance, error consequences, data quality, and intended use all affect how a model should be evaluated. The medical dataset in this chapter is an educational case study. It does not make our model suitable for diagnosis or healthcare decisions. For week 7, complete the assigned reading, watch the lecture and demonstration materials, complete the guided practice lab activity, and complete the independent practice assessment. In the next classification chapter, we will examine another supervised learning algorithm and compare how different models create decision boundaries.